Alright, some solved problems for Chapter 13. Starting off with unit conversion. Essentially, take 68 degrees Fahrenheit and convert it into Celsius. You can kind of see the equation I want to use right here. I'm going to say that my temperature in degrees Celsius is going to be 5/9 multiplied by my temperature in degrees Fahrenheit, 68 degrees Fahrenheit minus 32. Go ahead and do the math, and we're going to come out with 20 degrees Celsius. For part B, have a temperature in Celsius, want to convert that to Fahrenheit. I'm going to be using this equation right here. So temperature in degrees Fahrenheit is going to be equal to 9/5 multiplied by the temperature in Celsius, so 1900, and then plus 32, and we're going to get that's equal to 3452 degrees Fahrenheit. And here we have a question on thermal expansion. Essentially, we say that Eiffel Tower is made out of wrought iron, and we're going to treat it as just a 300 meter long iron rod, and say, okay, temperature changes between 2 degrees Celsius and 25 degrees Celsius. How much is the change in length going to be equal to? So change in length is equal to what? Well, we know that's going to be equal to the expansion coefficient times the original length times the change in temperature. So we know that it's wrought iron. We go ahead and look up the expansion coefficient for wrought iron. It's going to be 12 times 10 to the minus 6 per degree Celsius. Change in temperature simply going to be equal to 25 degrees minus 2 degrees. That's equal to 23 degrees Celsius. And so the change in the length is very simply going to be equal to 12 times 10 to the negative 6 multiplied by the original length multiplied by the change in temperature, and we're going to come up with 0.0828 meters, so about 10 centimeters. And now a problem with volume expansion. I have some glass, and it's filled with some initial volume of 450 milliliters. So I've got my 450 milliliter beaker, fill it up with water, and then I'm going to change the temperature. How much I'm going to change the temperature by? Well, I'm going to go from 100 degrees down to 20 degrees, so my change in temperature is going to be negative 80 degrees Celsius. The key thing to kind of keep in mind here is that the glass and water are going to contract at different rates. And so I'm going to have some volume that I could top this guy off with. So I could even say that the volume that I would add is going to be equal to the initial volume plus the change in volume for the glass minus the initial volume plus the change in volume for the water. And I said plus here because I'm expecting this change in volume to be negative because my temperature is going to be negative. Now you can kind of see here is I've got a positive V0 and I've got a negative V0, so those are going to go away. So the volume that I can add is simply going to be the change in volume for the glass minus the change in volume for the water. And I can use my change in volume expression to say, hey, look, the initial volume and the change in temperature is going to be the same. So this is going to boil down to the coefficient of volume expansion for the glass minus the coefficient of volume expansion for the water multiplied by the initial volume and the change in temperature. And now it's a fairly simple matter of just plugging everything in. 27 times 10 to the negative 6, that's the coefficient of volume expansion for glass, minus a much larger coefficient of volume expansion, so times 10 to the negative 6 of water, multiplied by the initial volume, 450 milliliters, and the change in temperature, negative 80. You can kind of see that this is going to be negative, that's going to be negative, and we're going to end up with a positive at the end of the day. And we're going to come up with 6.59 milliliters. And now for a little bit of volume expansion. We know that if we have a gas initially at some volume and it's at standard temperature and pressure, standard temperature and pressure, keywords for 1 atmosphere and 0 degrees Celsius, you heat it up 38 degrees, then you heat it up, you expect it to expand. This gas, any gas you see in this class, is going to obey the ideal gas law. PV is equal to nRT. One thing to be very careful of is this temperature right there must always be in Kelvin. So take temperature 1, you add 273 to it, and we're going to get 273 degrees Kelvin. You take 38 degrees, you add 273 to it, and you're going to get 311 degrees Kelvin. This equation will not work in Celsius. So very important, must be in Kelvin. Now what we can kind of do here is we can say, hey look, this product of the number of moles and the constant right there, that's got to be a constant. So I can say my initial pressure multiplied by my initial volume divided by my initial temperature is going to be equal to this constant. You can also say that's going to be true of the secondary pressure, secondary volume, and secondary temperature. So now I have a way to relate the initial parameters to the final parameters. With just a little bit of rearranging, I'm going to say that the second volume is going to be equal to the first volume, first pressure divided by the second pressure, second temperature divided by the initial temperature, just a little bit of algebra to get there. Initial volume is going to be 3.5. Got the ratio of the pressures, 1 to 3.2. And got the temperatures, so it's going to be 311 to 273. And we're going to get 1.25 cubic meters. You can kind of see that if you use this in Celsius, you'd get a very, very, very different answer. In fact, you would be dividing by 0, which we know we can't do. And just a little bit more practice using the ideal gas law. So we're looking for some pressure given a volume, a mass, and some temperature. One thing to keep in mind is this temperature right here must be in Kelvin. And also, if you use the value of R for I'm going to use, this volume must be in cubic meters. And we need to somehow convert this guy into moles. But at the end of the day, I'm going to say that the pressure is going to be equal to number of moles, gas constant, temperature divided by the volume. I know all these, I just need to get them into the right units. So let's start off with the temperature first. To go from Celsius to Kelvin, I add 273. So to go from 21.6, I add 273, I'm going to get 294.6 degrees Kelvin. I want to get this into something standard like cubic meters, and so what I'm going to do is I'm going to say, hey, I know that there's 10 to the minus 3 cubic meters in 1 liter, so my liters are going to cancel out, and now I have 38 times 10 to the minus 3 cubic meters. And lastly, the number of moles. I know the mass, so if I take that mass, 105 kilograms, tells me this is argon. Look in Appendix B and see that argon has a molar mass of 39.95, so that gives me this relationship right here. So if I want to go, essentially I just want to divide 39.95 mole per kilogram. You can kind of see how the units are going to work out. Kilograms are going to go away. I'm going to be left with the number of moles, which is going to work out to be 2628 mole. So now at the end of the day, my pressure is going to be 2628. Got my ideal gas constant, which is going to be 8.314. Got my temperature, which is 294.6. And I've got my volume of 38 times 10 to the minus 3 cubic meters. And I'm going to end up with 1.69 times 10 to the 8th pascals. And again, I worked everything in cubic meters, Kelvin, and number of moles. Used this expression 8.3. My answer for pressure should be in pascals. Just kind of some definitions with problem number 38. We know the definition of standard temperature and pressure, that 1 mole of a gas is going to occupy 22.4 liters, and now it's just unit conversion to get into molecules and cubic meter. So we know that there's going to be 6.02 times 10 to the 23rd molecules per mole, and that's going to allow me to kind of cancel that guy out. Now I simply need to go from liters to cubic meter. We know that 1 liter is 10 to the minus 3 cubic meters, so that's going to really cancel that guy out, and just multiply all that together. We're going to get 2.69 times 10 to the 25th. What unit is left is I got molecules over meter, so molecules divided by meter, and I have my answer. Quick little calculation on RMS speed. Given some temperature, we know that we can write the RMS speed as such. If we know 3, we know Boltzmann's constant, we know the temperature, we need to know the mass here. The mass, what it tells us is it tells us helium. Helium's got an atomic mass unit, or it's got 4 AMU worth of mass. So we take 4, we multiply that by the mass of a proton. Essentially we're saying it's got 2 protons and 2 neutrons, and now I have my mass. So really just kind of plug all this in. RMS speed is going to be equal to 3 times Boltzmann's constant, which is 1.38, give that 3, times 10 to the negative 23rd. Got my temperature, it's already in Kelvin, so I'm good there. So 6,000 degrees Kelvin. Divide all that by 4 times 1.66 times 10 to the negative 27th. And type all that in, and we're going to come up with 6116 meters per second, so about 6,000 meters per second.